That's very kind. Thank you. I appreciate the invitation. It's been so lovely to get to be here this week and meet you all. I am a mathematician, I am a modeler, and so I am going to give a math talk today. My apologies for the talk I'm giving is very different in title to what it said on the schedule, but I assume no one would be too upset about that. After our discussions this week, I thought it would be really nice for us to dive into some ideas behind opinion dynamics, because I think it's quite a relevant idea that's come up in a lot of across multiple rooms. We got to hear one lovely talk on it, but there's only been one. So I thought maybe another bit longer talk to think about opinion dynamics might be really generative for us looking forward in the next couple weeks. So I've given myself a challenge. I'm giving a maths talk, but I have tried to put in as few equations as possible. So my hope is that there's something here for everybody, and we'll try to keep it like not too boring and hopefully keep it kind of snappy, since I'm the only thing really standing between you and lunch, which is a challenging position. Okay, so let's set ourselves up. We're going to build from the ground up the idea behind the opinion dynamics models that I like to study. So let's imagine that we have some population, and this is our population on the screen here, these lovely like floating heads. We want to know in our population the evolution of opinions on some topic, any topic that we like. And for the purpose of this talk, I'm going to assume that those opinions can be quantified with some real number. So it says real value there. What I mean by that is you could pick any number along a spectrum from, say, 0 to 1, or I guess I've got on the slide here, -1 to 1. So maybe a concrete example would be if your view is, the most negative on a topic, you might be a -1. If you are the biggest fan of the topic ever, you'd be +1, but you could actually fall anywhere along that spectrum. To contrast this, you can imagine, and there are many models of opinion dynamics where you might take discrete values. So you might say, I have a 0 or a 1. I am interested in the thing or not. But here we're going to imagine we can take any value along some spectrum. Does that make sense? Are we clear? Okay, so what I've done is I've now given our little population, I've just generated them with some opinions. So these opinions are visualized in two ways. One is with the numerical value, and so that's how for or against the topic that they are. And the other is with the color, which is just matching the gradient, another way to visualize that same idea. So far, so good? Okay, so to mathematize this, what we might like to do is to create a variable that would store that value. Throughout the talk, I'm going to call that x sub I. So x is going to be the value. The little sub I, that's the agent's name. So I'll number them, 1, 2, 3, 4, however many there are there, 7, 8. And if we want that to change in time, that might be a function of time. Make sense? Good. Okay, do feel free to stop me. We can make this like a bit interactive. If you want to ask questions throughout, I'm very happy to do that. Okay, so now we've got a way to quantify and like mathematically formalize the idea of a population of opinions. But where it gets interesting is the evolution. So that's the dynamics. When I say dynamics, this is my field, dynamical systems. I really think of that as just systems that are changing in time. So let's start to imagine how this might happen for a population of individuals. And in opinion dynamics, it's very common to study the way that opinions change through interactions between the agents. So what I'm doing here in my little picture is I'm using a line to represent like possible interactions or relationships between agents. So you'll see that some of these agents have a line between them. So maybe they're friends or colleagues or in the same space in some way, and others don't. So they're not going to interact. They're not going to influence each other. Does that make sense? Good. Okay. So then we can use those interactions as a way to think about which agents will change which other agents' opinions. And then I'm going to take it to one more mathematical level of abstraction. What I've built here is what we would in math call a graph, or maybe more commonly in other fields you might call this a network. So the agents are going to be nodes or vertices in our graph. Those are the circles. And then the relationships or the possible interactions are encoded with edges in the graph. It gives us a really nice mathematical theoretical structure to think about our population. Okay, so now what we have, oh, one of our agents lost his opinion. Sorry about that. Okay, so now what we have, we've got our population, we've got their possible interactions, and we've got the opinions set. So let's talk about the dynamics. All right, this is one of my few equations. If you want, like I said, I won't show a lot of the equations, but anyone's welcome to come to me later. We can write down what any of these equations might look like. The general form tends to be something like this. So what I will do is I want to have an equation for each of the agents in my population. This is going to be an ODE. So I want to know what is the change of the opinion of agent I in time. That's what the left-hand side says here. And the right-hand side is some rule that tells me how I'm going to do that update based on what my neighbors in the graph are doing at that time. Okay, so there's a huge amount of flexibility there, right? I get to choose that rule. And there's that's the place where your modeling choices can really happen. I will tell you in just a minute the class of models that I like to study, but you can imagine this is a place where you can really play around and have a lot of fun. So just as one example, a super simple type of rule that we could have is maybe we start with that population that we seeded our opinions on the network, and then maybe my rule is just that every agent averages the opinions of all of its neighbors at every time. Okay, that's something we could write down mathematically pretty easy. And this is a type of system that's really well studied. What we know is that if you just run this forward in time, what's going to happen is that all of the nodes eventually will end up at the same opinion, which is like this network weighted average of all of the starting points. Okay, does that make sense? Cool. All right, so we've got a setup. I'm going to tell you about a particular class of opinion dynamics models in this general framework that I have been working on for the past 8 years or so. It's just given me a lot of mathematical joy. It's a very fun field. And we already got a really beautiful little introduction earlier this week. These are called bounded confidence models. And the first one I'm going to tell you about is the same starting point that Jacob mentioned before. This is due to Hegselman and Krauss. It comes from 2002. So relatively recently. And the idea is, okay, maybe not. If I said that to my students, they'd be like, no, that's forever ago. Anyway, the idea, the update rule that we're going to put on that right-hand side of our differential equation, our system of differential equations, is very simple. Every agent is going to do basically this averaging process. I look at all of my friends who I've interacted with, and I say, okay, how I'm going to update my opinion is just the average. We're going to try to come to a consensus. But here's the exciting catch. I'm only going to average the neighbors whose opinions are sufficiently close to mine. So I'm only receptive to opinions that are sort of similar. And this comes from a behavioral theory that's called selective exposure. So the idea is yes, we have some sort of pull as humans to come toward consensus, but we are much more likely, we're much more biased toward opinions that are similar to ours or that confirm our existing biases. Okay, so super simple way to do this that Hegselman and Krauss wrote down is that I just impose a hard cutoff. So here I'm going to walk through a little example together. My cutoff is going to be 0.5, and that's called my confidence bound. That's a parameter I could play with. I'll tell you in a moment what some consequences of changing that parameter are. Let's just say for now 0.5 is a cutoff. If the difference between my opinion and yours is less than 0.5 on the spectrum, we will average our opinions. Otherwise, I'm just not even going to listen to you. Too far away, too out there for me. You will not influence me. Make sense? Okay. So let's see how it works. I'm sure that I probably forgot to update or made mistakes in these, so don't caveat, you've been warned. I'm sure the numbers are probably wrong. So let's imagine what's going to happen. So we start with our initial population that I seeded in the example, and then what I'm going to do is cross out. These are all the interactions where like, yes, this is someone you might interact with, but these opinions are too different. Like, see this negative 0.9 and the 0.1, very far opinions apart, they're not going to influence each other. So actually, you've sort of reduced your effective network of possible interactions quite a bit by using this confidence bound. And so then the next step, what you're going to do is for all of the receptive edges that are left, we will do the averaging. Hopefully I did those right. Okay, so now this is our next time step. Now you could write this down either in discrete time, so you could say 1, 2, 3, or you could do it in continuous time and get differential equations. There's variants of both of these things, of these models. Okay, so let's carry on, right? We've gone one step, we could do another step. So now we could do the same thing, and you can't compare unless you have a very good memory, but you might notice because many of the agents moved their opinions, they may now become receptive to agents they weren't before, or they may have moved away and become not receptive, right? So we are not necessarily listening to or ignoring the same agents at every step. This is changing dynamically through this confidence bound. Okay, so we do the same thing, right? We're not receptive to some folks, we are to others, we average, and we have a new setup. Okay, so this dynamically is really interesting, actually. So I'm going to show you just a couple of possible qualitative behaviors that we can see from these models. So the pictures you're going to see here, there's a few. Let me talk you through them. The horizontal axis is going to be time, and the vertical axis is going to be the opinion state. So that, like, oh, sorry, now there's 0 to 1. So imagine 0 is the least, 1 is the most. That's on a vertical, and each colorful line is one agent's opinion over time. Okay, so I've got on the right pictures showing the networks with the colors. So those are equivalent to the pictures I was showing you in the setup examples. Okay, questions about these plots? Does that make sense? So I've got here 50 agents, and you'll see that just eyeballing it, that this top picture and this bottom picture, these are dynamically really different. Yeah, Jenny. Beautiful. Yes, you answered your own question perfectly. So you'll notice something kind of like tricky happening in this top graph. It's a bit counterintuitive, which is like this green line here. You think, well, this is very close to these other ones. How come it's not moving toward? And that might be because of the network structure. So maybe this agent here is not connected to anybody that they're receptive to, and they never meet anyone who they agree with, so they just stay the whole time. So there's several things that can play into the way the dynamics play out. One is, how do you see the initial distribution of opinions, right? That's really important. Here, you can see these are not exactly fair comparisons. I'm cheating a little bit. They're drawn sort of from a uniform distribution, but I've started with some clusters here. Here, they may be a little bit much more uniform. Okay, so that's one thing, initial distribution. The second thing is the network structure, right? Am I connected? Could I possibly interact or have a relationship or not? And the third thing is, how receptive are the agents, right? How different of opinions am I willing to listen to? And so this is a really important parameter. If I take this to be very small, my agents are not really too receptive, then it's much easier to get these very fragmented opinion states. So if I run the simulation for a very long time, I end up with something on the right where I have like several clusters of populations. So you might think about these as modeling like echo chambers or something like this, polarization, etc. As you increase the receptiveness, then these models start to just look like averaging, right? You listen to everyone, you're averaging. So then what you expect is something like what you see in the bottom where you come to consensus. So you can capture consensus and polarization dynamics even in this like super simple models. And then once you throw in that network structure of interactions, there's like this exciting additional spiciness, I guess. Okay, do you feel good on the setup? Yeah, fine.
I think that C is going to be the same for the whole population or same for the
That's a great question. So All of the things I'm going to talk about today, I'm keeping it homogeneous, so they are all having the same confidence bounds. But there are models, there are papers where folks look at heterogeneous confidence bounds. And actually, the talk we saw earlier, they're the confidence bound dependent on the opinion itself. So there's lots of like tweaks you could make to this parameter. Exactly. Yeah, exactly. So that could be something that's heterogeneous in the population. It could be dynamic. So you could really play with that. None of the stuff I'm going to talk about today does that, but it's a great observation. Cool. Other questions? Yeah, Ben. Yes, you can, and that I will briefly talk about. Yeah, yeah. This we can do also. There's so many. Something that I think is also really fun from just a modeling perspective is there's a lot of like dials we can turn, lots of levers to pull, right? A lot of cool modeling choices to be made. That's actually kind of a nice segue, I think, into what I'm going to talk the remaining of the time, which is I want to tell you about some of the projects that I've done, like ways I've kind of built upon or generalized or analyzed these models. And I'm going to highlight two that I think are kind of perhaps particularly interesting to the types of discussions that we've been having here this week. And then at the end, I will briefly like talk you through a couple more that if you're curious, you can read the papers or ask me later, but I won't go into detail. Okay, so the first one is about external forcing impacting opinions. So hopefully we're all kind of on board with what happens if we run these models with just the agents persuading each other. Lots of exciting stuff there, but one thing that my postdoc advisor at the time and I became very curious about was how if you have some kind of opinion that's being in some way injected into the population, how is that going to change the dynamics? Am I going to be able to like move the collective opinion in some way, or how much would it take to move the collective opinion? And so this was inspired in application by the idea, so at least in the States, our media environment is very politically polarized. So we were using media as sort of an example of an external forcing. You might have a very conservative media outlet that is sharing messages repeatedly with their followers, and that might be acting as like this additional source of influence. That's the motivation for this paper. So just as a reminder, what's the kind of thing that happens to these models? This is a Hegselmann-Krauss type model without external forcing. Okay, this should look sort of familiar. Here's what the agents are going to do by themselves, the way that I've calibrated the parameters of the model. Time on the horizontal axis, the ideology or opinion on the vertical axis, and again, the colorful lines, how it evolves in time. So here I actually took a network structure, which is a real social network. This is a Facebook network back in the day when Facebook was just on colleges. This is a particular small college in the US. And you can see that what happens is a pretty connected network. So most of the ideologies come to consensus, and there are a few outliers just due to the like structure of the network. Okay, so that's our baseline. So now let's start to ask, okay, what happens if we inject an ideology, perhaps like an extreme one, through these media? And how that's going to look is that I'm going to introduce what you might think of as like stubborn agents. So these will be additional nodes in the network. Blue is my persuadable nodes, and I'll add nodes to the network that never change their ideologies. They have some fixed ideology, and they're going to get some followers, which I'll just assign uniformly at random. So in this example, 2 media sources, 2 followers each. So what I'm going to do in the next couple of pictures that I'm going to show you is I'm going to see how the collective opinion changes when I add like more of these accounts with a particular opinion and more followers per account. So that's 2 ways you could imagine trying to like exert your influence. Does that make sense? Okay, now I'm doing something super simple here. I'm going to assume they're all like the same, so they're all going to have the same values. You don't have to do that. I'm going to assume they all have the same number of followers. You don't have to do that, but just for the pictures for today, that's what we're going to do. So let's see what happens. Here's a very small one. What if I have one node that has 1 follower? Okay, you'd expect this is like not a really big impact. And in fact, yeah, in this case, it's exactly the same. So I'm putting the media way up here. It's quite extreme positive at 0.9. And this, you see no impact at all on the dynamics. Okay, that's not surprising. Let's maybe we add more and we start to see some impact, we would hope. So, oh, I gave away, I should have done this in stages. It's more exciting. Sorry, I'm giving away the game here a bit, but what I'm showing is same figure on the left. The middle is, what if I have now more of these nodes, so 11, and many more followers, like 225 followers each. So we're getting some influence. And you can see, as you would expect, actually, over time, you're able to pull in like a great many of your population to that opinion. So they've changed quite dramatically from where they would end up otherwise, right? That's high impact. So then you might think like naively, okay, so surely adding even more, I will get even more, or I'll do it even faster. And in fact, that's not what you see. So a very interesting result from, and this is kind of one of the cool results I think of this paper. We go up to roughly doubling, this is like 21 sources, many more followers, 675 each. That's like 2/3 of the network each. You actually don't see as much impact. This is kind of a counterintuitive result. The trick, I've done a little sleight of hand here. If you're very observant, you might see on the horizontal axis, that sort of shows you the trick that's happening here. And I'm happy to talk through there's technical mathematical reasons why this happens, but the idea is that if your forcing is so strong, what happens is that those who are receptive to you get pulled in very, very quickly. And then what happens, if you get pulled in so quickly to that new opinion, the other folks get left behind. Whereas here, it's actually much more slow. Everybody comes close to consensus, and then they are collectively pulled by this more like moderate influence, which is kind of a cool, exciting result. I'm just showing you one example, but this is actually sort of robust. So you don't have to worry about the details behind exactly what the colors mean, but dark red is essentially like a summary statistic for higher impact. And you can see there is actually a sweet spot of if you're trying to heavily influence your network that you might like to do. And so we see this across various network structures. We see it across some various parameters. It's like relatively robust feature of these models. So kind of a cool way to think about external forcing and tuning the impact that, at least to me, when I first was doing these simulations, was a bit counterintuitive. It was a bit surprising to me. I was excited to see. Okay, so here's our takeaway. If you'd like to QR code, there's a QR code for the paper. I'll share the slides later, so don't feel stressed about getting it now. But the idea that you want to take away is that if you have these stubborn agents or some kind of other external forcing in your model, your opinion dynamics model, this can really change the dynamics, but not necessarily in the way that you might expect. So it can be, it is not always more effective to have more influence. That's something that you can tune a little bit. Okay, so that's the first one that I thought might be kind of relevant to the things we're talking about. The second is I want to talk about adoption and spread. So in everything I've talked about up to this point, I've thought about opinion dynamics models where everybody in the population is sort of just updating their opinions all the time. And I'm thinking about how everyone's opinion is changing. But sometimes the thing we care about is actually how a particular piece of content or behavior or opinion spreads throughout a network. So we might start with a network and then say, okay, will this person pass on their opinion to that person or not? And maybe it would change along the way, maybe not. And you might carry on and say, how many people will be impacted by the opinion? Do you see the difference between those two? Okay, so we're thinking spreading. Could you, just like you would do with a disease dynamics, the spread from susceptible to infectious and so on, could you do a spreading process, but then used a bounded confidence mechanism? And so that's what this paper is, and it's very in the spirit. I think that FE people will find this very familiar. And in fact, we all had a really nice introduction from Thomas yesterday about like branching process models in epidemiology, and that's just exactly the like mathematical guts that I'm using here, basically. So we all kind of have that mathematical background a little bit from yesterday. Okay, so I'm going to walk you through the example here just so we can understand the difference. Same starting point. I've got my network, and I've got, everyone's got their own kind of stance, their own opinion. And I'm going to start with some opinion that I care about tracking. So it's going to be the pink one, 0.1. And I'm going to set my receptiveness just like before, 3.3. So what's going to happen is nodes will adopt that content of their neighbor if the difference between the opinions is less than that value, C, 0.35 in my example. Okay, so what I'm going to do is start with the pink and then spread to the neighbors if they are receptive. Okay, so what would happen with my pink node is we have here two options, right? The 0.3 and the 0.8, but only the 0.3 is receptive. So the 0.8 one is just going to stay with their opinion, but the 0.3 will adopt the new one. Okay, so now 0.1, 0.1. Little different than before because I'm going to keep the 0.1 just for to think about it as really spreading. Okay, does that make sense? All right, so now next stage, 0.1 has quite a few neighbors. The three that are in pink are the receptive ones. So what's going to happen is in the next step, those three will adopt. And what we can do is we keep running this process until it terminates. And we are left behind with all of the agents who are receptive and adopted the content are in orange, those who don't are in gray. And so what you're ended with is what I call a dissemination tree. So this is basically starting at 0.1, that's the root. And then we have the tree that we could study. So we could ask a lot of questions about this. How many nodes adopt the opinion? What is the depth of the tree, right? What's like the longest path? What's the width? Like what's the most people that adopt in one step and so on. So we can ask lots of questions about this. I will just tell you very quickly, like a few results. So the nice thing about this setup, it's very simple, but it's really like you can pick up a lot of this branching process theory that's used in like SI models. And so what we can do is with these analytic arguments, we can actually think about what's going to happen at the early onset of what I'm calling the infodemic. So how quickly is it going to spread? And we could do this by creating what do I want to call it? I don't know, a number that is equivalent to R naught in epidemics. So we call it the opinion reproduction number. And it is really measuring the same sort of thing. So by calculating this through some branching process methods, you can get an analytic prediction, which is in orange, which you can see matches really nicely means from simulations. So you actually get pretty good predictions on how quickly this particular content will spread. Okay. You can also say things about the final size, like how many people will it spread to in the end. So what I've shown in the teal is histograms from actual simulations, and those vertical lines is what the theory predicts. So you can see we're actually hitting the means. Given that the infodemic happens, we can predict fairly reasonably how many nodes will adopt. So I think, leave that one there. There's some other kind of nice simulations in that paper where we notice some interesting themes about when you would see content spreading most widely and when the dissemination trees would be most long. But I'll leave that to you if you're curious to read about in the paper. So it's possible to think about modifying these sort of spreading processes to incorporate opinion dynamics models too. So it's another thing you can think about. Okay, what I will now do for the last few minutes of my talk is to tell you just a few more things that you may or may not find interesting that I have done with opinion dynamics models recently. And I will not go into any details. I will leave these for you or to chat about later. One thing that is of interest in many applications is everything I talked about so far is thinking just about pairwise interactions for opinion updates. But of course, in many scenarios, like what we've been doing here this week, your interactions might actually be in groups. And so a way to model that mathematically would be to think about hypergraphs instead of graphs. So instead of having an edge which just connects two nodes, you could have like a collection of nodes, which I've done with a little circle. We call that a hyper edge. Okay. So we could have like the yellow hyper edges, all those four together are like one group. And of course, you could have groups of two, which sort of, if you have only groups of two, that recovers graphs. So you can extend these bounded confidence models to hypergraphs. I have a paper with some wonderful grad students who we did some work on that. So if you are curious, there's that paper. This is one of my favorite papers in this area that I've done, but it's a little bit more theoretical. It actually gets to Ben's question really nicely, though. So the classical bounded confidence model is like either you're receptive or you're not. But you might like to say like, okay, well, maybe like the further away you are, like I'm going to weight you a little bit less, right? Until eventually maybe don't want to weight you at all. So with some collaborators, Phil Treadrow and Mason Porter, we decided to play around with this idea of like incorporating a weight function. So traditional version would be just ones up until C and then 0, but we've smoothed it out. And with a parameter, you could make it sort of really steep, or you could make it like really sort of a gradual decrease in weight. So of course, you can do this mathematically like pretty quickly, but the bulk of this paper is really, it's like theorems and proofs telling you that in various limits, you can actually recover the dynamic behaviors of these other models. So if I make my influence function here steep enough, it's going to look like a bounded confidence model. If I make it shallow enough, it's going to look like averaging. And so we prove various things about that, which, so those of you who like to see the proofs about those things, you may find this paper sort of interesting. And finally, this is quite recent work from my thesis student, Maddie Reeve. She looked at the impact of incorporating some different types of noise into these models. And she actually proved several conditions under which there's some types of noise that actually are consensus promoting. So there are certain types of noise where she's actually able to prove you are guaranteed to have your population come to consensus in these models eventually for certain types of noise. Eventually, though, is like could be arbitrarily large times. But there's some sort of interesting stuff there that's like hot off the presses just from May. And then ongoing work, this is also very theoretical, but thinking about with some collaborators, how you might take limits of these models. So in the limit that your network gets very large, you can actually write down what we call continuum limit, which gives you a PDE model that we could study, which has like, there's a lot of really nice theory you can leverage if you could find the right way to take these limits. And so I have some ongoing work on taking the appropriate limits of these models. Okay, so I'm going to finish up there since, lunch is going to soon beckon us. My pitch for this talk is that bounded confidence models, while they're simple and they're sort of a specific type of opinion dynamics model, I think they're also really flexible and they're really mathematically interesting. And so the questions I want to pose to you all to think about, and maybe things we can discuss in the weeks ahead, is for those of you who are working in particular domains, you have expertise in energy, epidemiology, elsewhere, like are these models useful in some way? Could they be modified? Could they be applied? Could they be coupled to other models that we're using? So I'm really just curious to hear your thoughts and see if there's any like interesting synergies there. Okay, so with that, I'm going to conclude. Here's the collaborators, the funding. Thanks for listening. It's been really fun. Thank you.